Okay, this is going to be the video for Calc 3, Section 15.5, applications of double integrals. So we'll talk about some of the ways that double integrals can be applied. Let me present here. All right, so yeah, double integrals and then later when we do triple integrals for three-dimensional space are very useful, especially in physics, but in many areas. And we're just going to look at some sampling of some of the uses for double integrals. So one is when we deal with mass and density. So density basically is how compacted material is. So highly dense material has a lot of mass in per area of region or volume. And then low density is just has less mass, right? So we can define the density typically given with a function rho for the density. If we have a two-dimensional, we usually call this a lamina, but like a thin sheet of something in the XY plane. Maybe it has areas where there's more mass and areas where there's less mass. Like let's say it was some sort of a styrofoam or something, and the molecules are packed more tightly in one region and less tightly in other region. There's more air in this region, there's less air in this region, or something like that, right? So we could define its density at any particular place x and y in two dimensions as the amount of mass or a change in mass for a change in area, right? An amount of mass per area, something like that, right? And that mass is varying. So if I wanted to figure out what the total volume or the total mass is, then I just need to sum up the density over the entire region. And so we define the mass as the double integral of the density over the area, right? Very straightforward. Okay, but there's also these things called moments. So a moment is defined as the product of a distance times some other quantity. And there's a lot of different moments and they have different uses. Some of the ones that are most common are the first moment of density, which is just called moment for material, is defined as the density times the distance from one of the axes. So in two dimensions, if we have two axes, then we actually have two moments, a moment for x and a moment for y. Right, so the moment for x is defined as the distance times the density, but the distance is from the x-axis. So the moment for x is the distance from the x-axis, but the distance from the x-axis is actually the y variable to that point xy. So if I have some point represented by this blue triangle here that has a position xy in the lamina here, it has a distance y from the x-axis. So the moment for x is the integral of the y times the density at xy summed with a double integral over all of the entire mass. Okay, that's called the moment in x. The moment for y is the same thing, except it's the distance from the y-axis. Therefore, it's got the x as the variable here. And it turns out that if you divide these moments by the mass, you obtain the position of the average of the material in the x and y directions, which is the location of what's called the center of mass. So there is some specific point, maybe it would be where this red dot is, where if you were to take this thin object and balance it on a pencil, it would perfectly balance if you positioned the object on the tip of the pencil at the center of mass, because there's an equivalent amount of mass in every direction from that. Right, so perfectly balanced. So this would be actually, since the moment in the y direction is related to the x distance, it's my here divided by the mass is the x coordinate, and the y coordinate is mx divided by the mass. Or you could just think of it this way. I just remember that this is the my over the mass, and this is the mx over the mass. So the first moment in y over mass gives me the x coordinate of the average position, center of mass, and the mx over the mass gives me the y. And so you can find my, mx, and m by computing three integrals, and then compute where the center of mass is of the object. And this is for two-dimensional object, or something which is approximately 2 dimensions. So that's called the first moment. The second moment is something called moment of inertia. And so that is if you take the distances from the axis squared multiplied by the density, and then at the particular point, and sum that over the region. So mass, that's the aspect of an object which resists linear force, meaning if in the equation F equals ma, Newton's law, right, for a particular force, you get a certain amount of acceleration, and the larger the mass is, right, the larger force is required to produce a particular translation, a particular linear acceleration. Well, the moment of inertia is the same thing, except for it's like rotational mass. So if you're rotating something, right, it's the aspect that tries to resist rotation, right? So that's called moment of inertia. And the moment of inertia around a particular axis is given by these equations here, depending on which axis the rotation is about. Okay, so like a flywheel has most of its mass at the outer edge, which it means it's hard to get it started rotating, and then once it is rotating, it's hard to get it to stop rotating, right? So that has a high moment of inertia. On the other hand, something where most of its mass is in the center of the object, that would have a low moment of inertia, right? So like on these discs that are being animated here, right? This disc here, the yellow disc, has a low moment of inertia because it doesn't take very much force to get it to roll very quickly, right? On this edge, we have things that have high moment of inertia, and it takes quite a bit of force to get them rolling, so they resist rotational motion. So the computation for that is whichever axis you're rotating around, you take the distance squared from that axis times the density and sum that over the entire object. Now, these are three-dimensional objects, but if you imagine these were thin laminas, something that was very thin, we could do that with a double integral around the axis, where this would be, say, the y, if we were doing this one. All right, so the second moment of inertia, or second moment is called moment of inertia. First moment is just called moment, but it's used in computation of the center of mass. So a physics application. There's other applications. One of them I just want to mention, Ms. Dastu didn't talk about this a lot last year, but I thought it was interesting. The book mentioned it, is in probability. So nothing physical, right? But there's something called a probability density function that you've probably been exposed to at some point in the past. I know you were if you took brief calculus. So if you have a random variable that provides a numerical value of possible outcomes of some sort of random process, let's say like you defined a random variable for the weight of an individual person. So if you selected a person at random from, say, the United States, W would be a random variable that contains their weight. And we expect the value in this random variable to vary from person to person when we take different samples of people, right? And maybe this variable could take on anything from 0 or almost 0 to some maximum weight. Like most people weigh somewhere between 0 pounds and 250 pounds, although a few people weigh up to, say, 800 pounds or something like that. Okay, so a probability density function, which is sometimes abbreviated a PDF, that is a measure of the likelihood of a particular weight occurring in a region. Right, so the height of this function represents how likely different weights are to occur in a population. And if you were to sum the area under this probability density function for all possible values, the integral of a PDF over its region is always 1, because all the probabilities add up to 100%. But if you wanted to find, say, the probability that somebody was between 90 and 150 pounds, and you actually had such a function here, you could take the just calc 1 type integral from 90 to 150 of that and find the area under the curve, and that would give you the probability of being in this region, because that's the fraction of the area of the total area of 100%, right? Or you could say what percentage of people weigh between 90 and 150 pounds, something like that. Okay. So the thing we're going to talk about here is that this probability density function is a function of just one thing, like the weight. What's the likelihood of a particular weight happening? But let's say I was investigating something like heart disease, and I thought heart disease depends upon two things, age, but also body mass index, right? So maybe I could find a probability density function for the probability of someone having heart disease, given that we know something about their age and about their BMI, right? So I have probability varying as two input variables. So I have a two-dimensional probability function, right? Multivariable probability function. So it would still be true that if I knew the entire extent of ages and BMIs, that if I summed the area under this surface, that would sum to a probability of 1. right? But now that would be a double integral, right? We would have to do a double integral, right? And moments are also defined for probability density functions, and they have interesting meanings. The first moment is called expected value. So in a standard PDF, single variable PDF, we knew that if we took the PDF and multiplied it by an extra x for the expected value, right, we got the expected value, which was the probability weighted average of the distribution of the whatever these things were, like say weights. It would be the probability weighted average weight. Okay. If we had a multivariable function, then you could find the first moments for either direction by taking the double integral and then find the average probability weighted average BMI and the probability weighted average age, right? So it would be an expected value for age and an expected value for BMI based on the two-dimensional probability function. So probability weighted expected values, but for two variables. That's the first moment of a PDF. The second moment of a PDF actually gives you variance. So if you take the distance or the value squared times the probability density function, you get the variance. And the variance, for those of you that have taken AP statistics, know that that's the standard deviation squared, which is a measure of how widely dispersed the data is around the expected value. So I'm just doing a single dimension variable here, but this would be a distribution that has a low variance, and this has a high variance, more spread around the expected value. The third moment of a PDF, this is a single dimension PDF, is actually called skewness, interestingly enough. And so that's how non-symmetrical the variation is. So high skewness is something that is very non-symmetrical. That would be a negative high skewness, and a positive high skewness has tails towards higher values, right? A low negative is slightly skewed left, and a low positive skewness gives you a measure of how skewed the data is, and a skewness of 0 would be perfectly symmetrical like a normal distribution, right? So deviation from symmetry, either in the tails positive or tails negative direction, is called skewness, happens to be the third moment of a probability density function. And there's actually a meaning to the fourth moment. If you take the data value to the fourth times the probability density function, it gives you something called kurtosis. And kurtosis is a measure of the tailedness of the probability density function. So for any variance, lower kurtosis means that you have more probability towards the central values and less in the tails, and higher kurtosis values are associated with more probability in the tails and less in the central area, right? So just kind of interesting that these moments have all these applications. So, we're not going to do a whole lot with these except for the physics ones, but I thought it would be interesting to mention that they appear throughout all different areas of science and math. Okay, but let's take a look at the physics ones, and we'll do a couple of examples here. So let's say we wanted to find the mass and the center of mass for a density that was given by x plus y for some lamina occupying a triangular region with these vertices. So first, we'd want to always graph that domain. So let's graph the domain. And we have the point 0, 0. And then, let's see, we have 2, 2, 1. And then 0, 3. So we have a triangular region in the domain here like this. And we want to find the mass of this if this mass varies. So we have to plug the x and y coordinates in. This mass is not constant. It's varying with x and y according to this. And so the mass would just be the integral, the double integral of the density itself over the area. So here, I think we could easily cover this with rectangular coordinates. Because I think I can come up with some simple formulas. This edge here would be, let's see, that's a slope of 1/2, right? So y equals 1/2 x. And this edge here would be y equals a slope of, what is that, -1 down 2 over 2. So -1, but with a y-intercept of 3. So it's easy for me to come up with functions of y in terms of x. So let's integrate this with dx dy. And we could cover this region. So they told me this was x plus y. And then we will use dx dy for the dA. And then let's see, the x's are going to go, well, let's see, let's do y first. Sorry. I would like to do y first. So I'm going to put my arrow this direction and integrate in the y direction first. We'll go from y equals 1/2 x to negative x plus 3. And then we have to integrate x values from 0 out to 2. So this would be the setup to compute the mass. Okay, now if we want to compute the center of mass, that means we have to take my over the mass and mx over the mass. So I also need to have integrals for my and mx. So let's go ahead and do the setup for those. Mx is going to be that same integral as far as covering the region, except that it's going to be the y direction times the density, and then dy dx, right? And then for mx, or my, we're going to do that same integral, same region, because we're still covering the same region in the domain, but this time x times the density, right? So, and then once we compute these, we can plug all these values into this expression to get where is the centroid, the center of mass, right, where we could perfectly balance this. Okay, so I'll just redo the setup. I'm going to ask you tonight to just don't look at this except to check your answers, but try it again and then check to see your setup is right, and then go ahead and compute what these values are. And you can use, well, I think these would be really easy to integrate. But all right, let's do another setup. A lamina occupies the part of the disk x squared plus y squared is less than 1. So that's a radius of one circle. R squared is less than 1, so R is staying under 1. In the first quadrant, find the center of mass if the density at any point is proportional to its distance from the x-axis. Okay, let's graph first to see what the domain area is that we're doing here. So we have a disk radius 1. Okay, disk radius 1. And it's the area inside that, but only in the first quadrant. So this is the region here. All right, so we're going to have to cover that somehow with an integral. But what's our density function? They didn't give us to us this time. So this time they're saying that it's proportional to the distance from the x-axis. So the distance from the x-axis is actually going to be y. So it's proportional, meaning there's some constant times y gives me the density. Okay, k is some constant of proportionality. That means my setup for m is going to be an integral of the density, which is ky. And then now on this case, I think probably I would not want to, well, let me just do dA for a second. And then let's figure out, probably should cover this with polar coordinates. Wouldn't you agree? Polar would be better. Let's do polar, because that way I can just go from r equals 0 to r equals 1. And then to cover this, I could go from theta equals 0 to theta equals pi over 2. That would be really easy for this, right? So what if I did this? What if we said, okay, this is going to be k, but then for the y, we would have to substitute r sine theta. And then I have my rd theta because it's polar. And then let's do the radiuses. That would go from 0 to 1. And the theta is from 0 to pi over 2. So not too bad. You should probably even be able to do that one by hand as well. But if I want the center of mass, I'm going to also have to have mx, which is that same pi over 2, 0, 1, k, r sine theta. But remember, we have to also multiply by y, right? So what's going to happen here is I'm going to have to insert another y, and the other y is also going to be r sine theta. And when you do my, it's going to be the same, pi over 2, 0 to 1, k, r. This is the density part, but we're going to have to insert a y, an x, and the x here will be r cosine theta. Okay, now we're getting up into the region where this might be pretty tricky. This part is x here. It might be pretty tricky to do that by hand, but maybe not. All right. So, and then the to finish the problem, the center of mass, x bar, y bar, would be my over mass, mx over mass. Okay. All right. Okay, let's do the next one. So that's the setup. Try that setup again, right? And then do the integrals for homework. Number 12. A lamina occupies a part of the same thing, first quadrant, center of mass, if the density is proportional to the square of its distance. Okay, so the only thing changes here is that the function for the density is no longer ky. It's the distance from the origin. Well, the distance from the origin is just the radius. So we're going to redo this except with distance from the origin. So same setup as far as the integrals, right? We'll have 0 to pi over 2. Let's see, 0 to 1. But we'll have kr for the density, and then rd theta. For mx, we'll have 0 to pi over 2, 0 to 1 density. And then I'm going to have the extra y this time. Y is the distance for the x, so that's going to be an extra r sine theta, rd theta, right? Where this is the rho, this is the y, this is dA, all right? And then my would be 0 to pi over 2, 0 to 1, kr, but this will be r cosine theta, because for the my we have to have the x distance. So this is rho, the density, this is the x, and this is the dA. Okay, and then again, the x bar, y bar would be my over m and mx over m. That setup's not too bad. Give that a try again. And then I had one more here, so this one looks a little bit more involved. Okay, let's see. A lamina occupies a region inside this circle, but outside this circle. I was going to go on these circle inside a circle things. Okay, let's graph it. So this one is a circle of radius 1, right? So, and centered at the origin. So I think I can do that. Circle of radius 1. Okay. This one we'll have to do a little completing the square business. X squared plus y squared minus 2y equals 0. X squared plus y squared minus 2y something equals 0. Let's complete the square. So completing the square, cut this in half, get -1, square it. That's 1, add 1 to balance. So it looks like we've got a circle that's centered at 0, +1. So the second circle is centered here, and it also has a radius of 1. Okay, so here's the second circle. And lamina occupies the region inside the red circle, but outside of the blue circle. All right, so it's this region here, right? Yeah. All right, and the density is proportional to distance from origin, which is going to be some constant times r. All right. All right, so center of mass, we're going to have mass first. Let's do that. So obviously we're going to do polar. I think we should go from radius to radius here. So let's see, for the blue circle, we've got the relationship that x squared plus y squared equals 1, which is r squared equals 1, which is r equals plus or minus the square root of 1, which is r equals 1. So yeah, we already knew that. R is 1. But for the red circle, we've got, let's see, x squared plus y squared equals 2y, which is r squared equals 2r sine theta, which means r squared minus 2r sine theta equals 0, which means r times r minus 2 sine theta equals 0, which means if r isn't 0, then r minus 2 sine theta must be 0, which means r is 2 sine theta. So that's the radius at the stopping point for the radius. So it looks like we have a double integral again, and we've got, just for the mass, just the density, which is kr. And we're going to have r d theta. But the r is going to go from r of 1 to r of 2 sine theta, right? Now, how do we determine where this starts and ends? This might be even trickier, right? Where do we start and stop this? Where is this intersection? Okay, well, let's work on an intersection. For the intersection, what if I took, because I want everything in terms of r with theta. What if I took these two equations, r equals 1 and r, let me just do the intersection in polar coordinates. So we have r equals 2 sine theta, but then r must equal 1 at this intersection point. So if I just substitute that, I get 2 sine theta equals 1, or sine theta is 1/2, right? Which on a unit circle, sine is a half, y is a half when we're at pi over 6. Is that right? Pi over 6, yeah, because this is square root of 3 over 2, 1/2. Sine is 1/2 at pi over 6. So this would be pi over 6. And by symmetry, this would be pi minus pi over 6, or 5 pi over 6. So it looks like I have to go from pi over 6 to 5 pi over 6. And that would be my integral for finding m, right? To find mx, we would have the same integral, pi over 6 to 5 pi over 6, radius from 1 to 2 sine theta, kr, but we have to have the extra y. And so the extra y is r sine theta with r d theta. And then my would be from pi over 6 to 5 pi over 6, 1 to 2 sine pi. There's the density, but now we want the x, so r cosine theta, r d theta. And then the center of mass would be my over m and mx over m. All right, so fair amount of actually computing to get where that is numerically, but see if you can find that too. All right, so those were difficult enough. I thought we definitely need to go over the setup before you can try the homework. But try the setup again just from looking at the problem, and then check your answer. And then when you verified the setup, then go on and do the actual computation. All right, that's it for 15.5.